Okay, so let's just take the basic ball on a string going in a circle that we just saw. And so here's my terribly drawn circle. Whoops. Oh, hold on. I forgot I have a circle function. And so let's just say that we have a ball on a string, or a person running around a track. So it could be a top view, or a merry-go-round, top view, Ferris wheel, side view, whatever. So we got something going in a circle. So here's my object, and let's just say it's a ball on a string. And that ball is anchored at the center in the string, and the ball is moving. Let's just say the ball is moving in that direction. It's going around the circle in that direction. Okay. So what are the various things that we can describe about this circle? Well, we saw that there's describe the radius of the circle, of the circular motion, right? The radius of the circle. And this is where, even if it's going in a complicated motion, if you're following some, curvy roads, at any point on those curvy roads, you can assume, right, you can just draw a little arc here, and you can say, okay, well, that circle has a certain radius r. Now the curvy road may have a different kind of arc here with a larger radius r, right? So, but you can always break it up into little pieces and assume that if you're going around a corner, you're sort of going in circular motion. Okay, come back to our real circle. We're going to stick with good circles. And we've got the circumference, right, of the circle, right? The circumference, circumference. And we all learned in third grade that the circumference of a circle is 2 pi r. 2 pi r. That's the distance of one full rotation, right? I won't write those words down, but you should. It's the distance of one full rotation. So if the ball starts where I show it initially, and it goes all the way around the circle, and it gets back to where it was, and so it gets there, and we ask how far has it gone? It's gone a distance of 2 pi r, whatever the radius of the circle is. We could say if there's a ball on a string, maybe my string was about 1 meter long, so it's going to be about 6 meters total distance, right? 2 pi r, 6.28 meters. But what's the displacement? What's the displacement when the object goes in a full circle? The displacement, delta x or delta y or delta d, whatever you want, the displacement is 0, right? Because it starts where it finishes, and displacement is just final position minus initial position. And so for something going in circular motion, it will go a distance of 2 pi r in a full circle, but it'll have a displacement of 0. So we're just talking about the kinematic variables and how we can describe the circular motion using distance, displacement, velocity, speed, and acceleration. Now, so we can talk about the object's velocity at any instant, right? Now, what happens to the object's velocity as it goes around the circle, right? At any instant, the object is going in its forward direction. It's going in that direction. But it keeps on changing direction, right? Sometime later, this ball on a string, right? Sometime later, it's over here, and for some reason it got smaller. But anyway, that's relativity for you. And so its forward direction has changed, right? So its direction is changing. Its direction is changing. So that means that since its direction is changing, its velocity is changing as it goes around the circle, because the velocity is both how fast it's going and the direction that it's going. So if we call this the velocity vector, right, v initial, or we'll just call this v1, at some later time, this is the velocity vector v2. Why is it pointing in the forward direction? Because at any instant, that's the direction it's moving. It's moving in its forward direction. It's moving tangential to the circle. But that string is continually pulling it in, so it's not letting it go. Imagine this ball going in a circle and cutting the string. And don't worry about gravity or anything. Pretend we don't have any gravity. Imagine cutting the string at v2. I mean, when it's in the second position, and the ball is just going to follow. Right, it's going to follow that v2. I'm not drawing terribly straight, but it's going to follow that line if we cut the string, right? It'll just go straight. So basically, you can say if an object is going in circular motion, It must be doing so because there's some force keeping it in the circle. But if you take away that force at any instant, what direction is the object going to travel? And some of you, I guess, would say this way. But we'll discuss this more when we get to the force chapter. But what you need to think about is what direction is the body going in? It's going in the tangential direction. So and the only reason why it keeps on changing to a new tangential direction, like later on it's going in this direction, later on it's going in this direction, later on it's going in this direction, is because there's some force that's keeping it in that circle. We're not talking about forces today, that's for the next chapter, but just you do have to understand that there are forces keeping it in the circle, but its direction of motion is tangential to the circle. Yes, I changed the color of the object. Also, I guess that it is just an ever-changing object. Okay, so we understand that the velocity is always in the tangential direction. And then I shouldn't ask. Well, I guess since I said so, I will ask. Does the velocity, I'm going to ask a stupid question. Does the velocity change as it goes around the circle? Sorry. Let me step back for a second. The one thing I didn't define is the difference between circular motion and uniform circular motion. Circular motion is an object going in a circle. Any radius, at any speed, it might be changing speed. Uniform circular motion. What does uniform mean in uniform circular motion? What does uniform mean in uniform circular motion? Uniform means constant speed. It doesn't mean constant velocity. Those are two very different things, or they're two different things, certainly. Uniform means constant speed. So when we're talking about uniform circular motion, we're talking about an object moving in a circle or going around a corner at constant speed. Can an object go around a corner or move in a circle at constant speed? Absolutely. I can be running at 3 miles an hour and I can get on a track and I can run at 3 miles an hour around and around that track. But the reason why this is constant speed and not constant velocity is the discussion that we just had, that your velocity is continually changing. Regardless of even if your speed is constant, your velocity is continually changing because your direction is continually changing, because your direction is always tangential to the circle. It continually changes as you go around. So your velocity changes as you go around the circle at constant speed because the angle changes. Let's just define a couple of other quick variables here. Of course, just in case you forget, we've got we had the radius. Radius vector, by the way, we will deal with radius vectors, start from the center of the circle and point towards the edge of the circle where the object is. But really all we care about here is the radius, the magnitude of the radius vector. The diameter is twice the radius, right? It's the maximum distance from one edge of the circle to I don't know. It's twice the radius. It's the line that goes through the center of the circle, that goes from one side of the circle to the other. So that's the diameter that I just drew there. I'm not going to talk. There is no such thing as a diameter vector. That's the diameter. I shouldn't have put arrows on it. Diameter, radius. What about the amount of time that it takes an object to go in a circle? So let's say that this object starts again from where you see it, and we go around the circle. We start the stopwatch when it starts, and we go all the way around the circle. Whoops, hold on. Sorry, try again. So we start the stopwatch, go, and we time how long it takes to go around the circle. We time how long it takes to go around the circle. That amount of time for one complete revolution is called the period. So period, I'm writing messy. Yeah, I think I fixed my problem. Period is defined as the capital letter T, and that is defined as the amount of time for one complete revolution. Amount of time for one complete revolution. And notice if we're talking about uniform circular motion, so that's the definition of period. For uniform circular motion, then the period is a constant, right? Because it doesn't change speed. It's going to take the same amount of time every time. It doesn't change speed. So the period is a constant. Okay. We can define the frequency. Frequency Oh, what are the units of period? The units of period are it's just a time, so the units are second. Let's go ahead and define frequency. Frequency is the number of times you go around per unit time. It's actually defined as the number of cycles per unit time. And what that means for circular motion, I'm going to write over to the left a little bit, that frequency is equal to a cycle is a revolution. So, whoops, I'm going to get rid of the number sign. It's revolutions per amount of time, or revolutions, it's revolutions per unit time. Revolutions per unit time. That's the number of cycles per unit time. So if we're talking about time in seconds, right, MKS units, then it's going to be revolutions per second would be the units of frequency. So what is what is the relationship between frequency and period? Well, if period is the amount of time for one revolution, so it's time per cycle. Period is time per cycle, and frequency is cycles per time, then frequency is just 1 over the period. Frequency is 1 over the period. Okay, what are the units of frequency again? The units of frequency are revolutions per second. But revolution, this is a tricky one sometimes. Revolution is a unitless quantity. It's a number. The number of revolutions, right? It's a unitless quantity. So the units of frequency are actually, you can definitely write revolutions per second. There's no problem with that. But it is also 1 over seconds, right? The units are also 1 over seconds, because revolution, let's just take a step back here and think about what a revolution is. Revolution is actually an angle. It's actually an angle, right? One revolution is 360 degrees. It's also 2 pi radians. Right, so let me write that down. 1 revolution equals 360 degrees equals 2 pi radians. This is geometry of a circle. Hopefully you remember that from 3rd grade. Kidding, I know, it was last year or whatever. Maybe you never learned it, but these are angles. So a revolution is actually an angle. And if you remember, you might remember that angles are actually unitless quantities. They're unitless quantities, meaning they're just a ratio of 2 distances, right? An angle is defined as, I just added a couple words here, just talking about angles. An angle in general, right? An angle that you go through when you're going around in a circle or any kind of revolution is defined as the arc length. You might or might not remember this from math, divided by radius. Arc length is, I'm going to go back to the circle again, for this angle theta, the arc length here, right, this arc length is S, and theta is defined as S over R. That's the angle. It's a ratio of 2 distances, so it has no units. And so therefore an angle can be, we can say degrees per second. So now going back to my units of frequency, we can talk about degrees per second, revolutions per second, radians per second, but all of those angles are unitless quantities. So we can also write it as just 1 over seconds. So the units of frequency are 1 over seconds, which is defined as the hertz. The hertz, the unit of frequency is the hertz. 1 over is revolutions per second, radians per second, degrees per second, whatever. 1 over seconds is the hertz. What else was I going to say about that? But sometimes we need to be careful about how we're measuring our angle. It might be more sensible to say radians per second, degrees per second, or revolutions per second, because the hertz is actually I'm going to leave it at that. The hertz is 1 over seconds. So there we've defined all of the variables which describe the motion, right? We've defined all the variables that describe the motion. But now let's derive another variable which we need for the kinematics, which is the acceleration. That comes next.